Imagine a single comma in a spreadsheet costing a company millions of dollars. Or, I mean, just a simple program crashing an entire server network because, well, someone forgot to close a digital door behind them.
Yeah, it happens way more often than you'd think.
Right. Today, for you listening, we are looking at the digital blueprints of how your computer actually reads and writes data. And why a simple typo or a misunderstood command can just bring a whole system crashing down. Welcome to another deep dive.
It is great to be here. Thanks for having me.
Of course. So our mission today is to demystify the invisible infrastructure that makes your software work. We're looking at this highly concentrated stack of presentation slides from a lecture on Python programming. The specific topic is file I/O.
Right, which stands for file input and output.
Exactly. And right up front, I'll admit, looking at these slides, they're dense.
Oh, they are. Yeah, if you just glance at them, it looks like this sparse list of isolated vocabulary words.
Yeah, just random terms.
Exactly. You see terms like list, open, with CSV and PIL, but they aren't just a glossary. What we are really looking at here is a map.
A map.
Yeah, it is a complete logical journey tracing how data flows. It's the story of how raw information rests on your hard drive, gets securely pulled into a program's active brain, I guess you could call it,
Right.
gets organized, manipulated to handle real-world chaos, and finally interacts with the physical reality of our screens.
Okay, let's unpack this.
Mm.
Because even if you, the listener, have never written a single line of code in your life, the concepts here are universally applicable to understanding how every app on your phone or computer actually operates.
Absolutely.
So to understand how a program handles data,
Right.
we logically have to start at the absolute beginning of that flow, right? The gateway.
Yeah, the front door.
Right, because you can't process a file until your program actually gets its hands on it. And the slides start with what seems like the most intuitive command possible, the open function.
Exactly. And the slides specifically point us to the official Python documentation for this, which lives at docs.python.org/3/library/functions.html #open.
Quite a mouthful.
It is, yeah. But the reason open is the foundational gatekeeper here is because your computer operates in two very different physical spaces.
Okay.
Your active program lives in the computer's fast, volatile memory, the RAM,
Right.
but your files, your actual documents and photos, those live in long-term physical storage on the hard drive.
So they're completely separate.
Exactly. And the open function is the bridge between them. It is the program formally asking the operating system for a ticket to access that specific piece of data.
I picture this literally like using the open command is like unlocking a heavy door to a secure room where the data lives.
I like that.
Yeah, you put the key in, you turn it, the door swings open, and now you can see the file sitting on the table inside. But here is where the slides introduce a bit of a twist. Right after the open command, they heavily emphasize a different keyword, which is with. And I have to ask, like, why do I need a special extra keyword just to look at my data?
Right.
If I open the door, can't I just walk in?
Well, it is a fair question, and it really gets to the heart of what software engineering actually is. What's fascinating here is that in programming, opening a file is a massive responsibility.
Because it's a secure room.
Right, because you are claiming a finite resource from the operating system. Let's stick with your door analogy. If you unlock the door, go inside, read the files, and then your program just, wanders off to do something else without actively closing and locking the door behind you,
Yeah.
what is the consequence?
Well, I mean, the room isn't secure anymore. I guess another program could wander in and mess with the files while I'm not looking.
That is part of it, yeah. The file becomes vulnerable. But the bigger issue is a total systems failure.
Wait, really?
Oh, yeah. A lot of people mistakenly think leaving a file open just eats up RAM or causes a memory leak. But it's actually much more catastrophic than that. It creates a resource leak. Specifically, it exhausts what we call file descriptors.
File descriptors, what are those?
Yes, file descriptors. Your operating system only has a limited number of tickets it can hand out to programs to access files simultaneously.
Oh, I see.
So if your program loops through a folder and opens 10,000 files, but forgets to give the tickets back by closing them, the operating system literally runs out of tickets.
And then what happens?
It panics. It will refuse to open any more files for any program, and your entire system can just crash.
Wow.
Furthermore, the operating system places a lock on open files. If you leave it open and the user tries to delete the file or another program tries to update it, the computer will just throw a stubborn error saying, sorry, this file is in use by another program.
Oh, I hate that error.
Yeah.
So as a developer, I have to manually remember to write a command to lock the door every single time I open one,
That's the old way, yeah.
because I forget to lock my actual apartment door half the time.
Yeah.
That sounds like a disaster waiting to happen.
And developers are humans, so they forget too. That is exactly why the with keyword was invented. The slides emphasize with because it acts as what Python calls a context manager. It is essentially a built-in, foolproof safety net.
How does it work, though? Does it just automatically close the door behind me?
Exactly that. When you write code saying you want to open a file with this command, you are creating a temporary context block.
Okay.
You are telling Python, look, I need to go into this room for a minute. While I'm in here, let me read the files. But the absolute second I step out of this specific block of code, I want you to automatically slam that door shut and lock it.
Oh, that's brilliant.
It guarantees the file is closed no matter what happens. Even if the program encounters a massive error while reading the file and completely panics and crashes, the with statement ensures the file ticket is handed back to the OS on the way down.
Okay, that is actually a huge relief. It turns a manual, error-prone chore into this automatic safety mechanism. So, open grants access, and with sent, manages the safety of that access.
Yes.
That is incredibly smart defensive engineering.
Precisely. It ensures your program is a polite and responsible citizen of the computer's ecosystem.
Right. Okay, so the door is securely locked behind us, the ticket is returned, and we have safely pulled the data into our program's working memory. But right now, that data is just, a chaotic, raw stream of text.
Right, it's just a blob of characters.
Yeah, so we logically need a place to put that information and a way to make sense of it. Which brings us to the next structural step in the slides, the list concept and the sorted function.
Right, because getting the data is only half the battle. Now you need a data structure in your active memory to hold it securely.
I think of a list simply as a digital filing cabinet, or maybe a long row of numbered moving boxes.
That's a good way to picture it.
You dump the first line of the text file into box number 1, the second line into box number 2, and so on. It gives the chaos a strict order. We don't really need to dwell too much on what a list is, because the really interesting part is what happens when we try to organize those boxes.
Yes, manipulating the list is where the real logic begins.
And slides point us to the sorted function for this. But here is where we hit a wall of intimidating technical jargon.
I know exactly what you're going to say.
The slides link to the official documentation, docs.python.org/3/library/functions.html #sorted, and they specifically display the technical signature of the command.
Yes, they do.
Let me read this exactly as it appears. It says, sorted, open parenthesis, iterable, comma, / comma, asterisk, comma, key equals none, comma, reverse equals false, close parenthesis.
Yep, that's the one.
I have to be honest, looking at that / and that asterisk right in the middle of the command, it looks less like a helpful instruction and more like a typo.
It definitely looks alien at first glance, and this raises a really important question about how we interact with technology. Reading documentation is a distinct skill, entirely separate from writing code.
It really feels like it.
You are looking at the rigid grammar of the machine, but once you understand how to decode this specific sentence, it unlocks the ability to read almost any technical documentation.
Please decode it for me, because the punctuation is making my eyes cross. Let's start with the actual words before we get to the symbols.
Fair enough. The first word is iterable. That is simply the thing you want to sort. In our case, it's the list of data you just pulled from the file.
So, my moving boxes.
Exactly. You are handing the function your row of numbered moving boxes.
Okay, that makes perfect sense. Here are the boxes, please sort them. What about the end part? Reverse equals false.
That is just a default setting. It's telling you that out of the box, it will sort things in standard ascending order, A to Z or 1 to 100. If you wanted it to sort backwards, Z to A, you would explicitly tell the function reverse equals true. It is just a toggle switch you can flip.
Got it. And the key equals none part.
That is a placeholder for custom rules. By default, it sorts alphabetically. But what if you wanted to sort a list of names, not by the alphabet, but by how long the names are?
Like character count.
Right, you could plug a custom rule into that key slot.
Yep.
You're handing the function the specific key to understanding how you want this organized.
Okay, so iterable is the raw stuff, key is the custom rule, and reverse is the direction. The words make sense, but you were dodging my main question.
I'm getting there.
What about the weird punctuation? What are the forward slash and the asterisk doing sitting by themselves in the middle of all that?
The punctuation. So this is where we get into the philosophy of how an API, an application programming interface, is actually designed. This isn't about what the function does. It is about the strict rules of how a developer is allowed to talk to the function. The forward slash and the asterisk are dividers. They divide the arguments into different behavioral categories.
Think of it like ordering at a drive-through. Does the slash mean one thing and the asterisk mean another?
Exactly. Let's use that analogy. That's great.
Yeah.
Anything before the forward slash, in this case, our iterable list, is what Python calls a positional only argument.
Positional only.
Right. Think of it like ordering a standard combo meal at the drive-thru. You just say, I'll have a number 1. You don't need to explicitly say combo meal name equals cheeseburger.
Right, yeah.
The cashier knows exactly what you mean, purely based on the position of the number you said. So in code, you just hand the computer my list, and because it is the very first thing you handed over, the computer knows, this is the iterable thing to sort.
Oh, I see. So the slash means everything before me doesn't need a name tag. Just hand it over in the right order.
Yes. But now look at the asterisk. Anything after the asterisk is a keyword-only argument.
Keyword only.
Going back to the drive-thru, these are your custom modifications. You cannot just pull up and shout, no pickles or true or none, and expect the cashier to guess what you mean.
They just stare at you.
Exactly. You must explicitly name the modification. The asterisk forces the programmer to explicitly type out reverse equals true or key equals my custom rule.
So the asterisk says, everything after me absolutely must wear a name tag, otherwise the computer will reject it.
Exactly. And the reason Python's designers force this rule is to prevent catastrophic downstream bugs.
Also,
If you just passed a random true into a complex function, another programmer reading your code 6 months later would have absolutely no idea what that true is actually toggling. By forcing you to write reverse equals true, the code becomes instantly readable, and it prevents you from accidentally flipping the wrong switch.
okay, that is actually a huge relief.
Yeah.
It turns the documentation from a foreign language into a strict set of traffic laws. It's all about making the code safe and predictable.
Exactly. The documentation isn't trying to confuse you. It is showing you the unbreakable laws of communication for that tool.
So we've safely pulled the data in, we've stored it in a list, and we've learned the strict grammar required to sort it. But sorting flat lists of text is fine for a basic grocery list.
Sure.
In reality, the data you and I interact with every day is rarely just a single string of words. We are dealing with massive, complex tables of information, spreadsheets, financial records, customer databases.
The heavy stuff.
Right. And this brings us naturally to the next phase of our data flow,
Yeah.
dealing with CSV files. Here's where it gets really interesting.
Right. CSV stands for comma-separated values. It is basically the universal language for moving tabular spreadsheet data around the internet.
And the slides point us to a dedicated Python library simply called CSV, linking to docs.python.org/3/library/csv.html. But here's where I want to push back a little, because I see a potential complication that feels totally unnecessary.
Oh,
Well, the name literally tells you what it is. Comma-separated values. It's just a basic text file, and every time there's a new column in the spreadsheet, there is a comma.
right.
If we already know how to use open to get the file, and we know how to put it into a list, why do we need to learn a whole dedicated library just for this? Couldn't I just write a simple rule that says, hey, Python, read this text file, and every time you see a comma, just take out your digital scissors and chop the text into a new column? Why overcomplicate it?
I am so glad you brought that up, because that exact logic, the whole I'll just chop it with scissors approach, is a trap that almost every single junior programmer falls into.
Wait, really?
Oh, yeah. It makes perfect logical sense until it collides with the messy, unpredictable reality of human data.
Messy how? A comma is a comma.
Let's test that theory. Imagine you are processing a spreadsheet of international customer records. You have 3 columns: name, street address, and city.
Okay, simple enough.
If you tell your program to blindly chop the text every time it sees a comma, what happens when a customer's city is listed as Paris, France?
Oh,
Yeah.
I see the problem.
Right. The data value Paris, France contains a comma inside the actual value. If you use your blind scissors approach, your program chops that single geographical location into 2 separate columns.
Right, because it sees the comma.
Exactly. Suddenly, France shifts over into a 4th column that doesn't exist, pushing the next row's zip code into the phone number column, and your entire database of 1 million customers is completely corrupted, all because of one rogue comma.
The dreaded rogue comma. Wow. So how does a computer actually know the difference between a comma that means start a new column and a comma that just means Paris, France?
This is where the CSV format gets surprisingly complex behind the scenes. When spreadsheet software, like Excel, saves a CSV, it looks for commas inside the data. If it finds one, it wraps that entire specific cell in quotation marks. It saves it in the text file as, quote, Paris, France, quote. The quotation marks are a structural signal telling the computer, hey, ignore any commas you find inside this box.
But if I just wrote my own simple scissors code, my program wouldn't know to look for those quotation marks. It would just see the comma and chop it anyway.
Exactly. And think about what it takes to write a program that does look for those quotes. You would have to write custom code that reads character by character, maintaining this complex state machine, constantly asking, am I currently inside a quote block? Or am I outside a quote block?
That sounds exhausting.
It gets worse. What happens if the data actually contains a quotation mark inside the text? Or what if a single spreadsheet cell contains a multi-line paragraph with line breaks inside the quotes?
That sounds like an absolute nightmare to try and code from scratch.
It is a total nightmare. And that is exactly why the built-in CSV library is such a marvel of software engineering. You don't have to reinvent the wheel or write hundreds of lines of edge case logic. Python's developers already fought those battles for you.
Thank goodness.
Yeah, the CSV module is a battle-tested tool built specifically to safely decode all that real-world chaos.
Okay, so there's a crucial distinction here. CSV, in capital letters, is the universal, surprisingly tricky file format. And CSV, in lowercase letters, is Python's specific software tool engineered to safely navigate the minefields of that format.
Perfectly stated. It takes the entire burden off the developer. You securely open the file, hand the raw data to the CSV library, and it hands you back perfectly organized data, completely immune to rogue commas and hidden line breaks.
That makes a lot of sense. It really highlights how much of programming is just, defensive engineering against unpredictable real-world data.
Yep.
Now, as we move to the final concepts in our source material, we have to make a bit of a leap. We've successfully flowed from raw text to organized lists to complex structured spreadsheets. But File I/O isn't just about text characters.
Not at all.
When you look at your hard drive, most of the space is taken up by media. Photographs, audio, video. And the slides reflect this reality by introducing the letters PIL and a URL.pila.readthedocs.io. So what does this all mean?
Yes, this is where we bridge the gap from text processing to binary multimedia. Because to a computer, a high-resolution photograph isn't a picture. It is just a massive, complex file filled with binary data representing millions of colored pixels.
So how does everything we've talked about apply to a photograph? And before we get into the technical side, I noticed a discrepancy in the sources.
Oh, what's that?
The big, bold letters on the presentation slide say PIL, but the documentation URL clearly says pillow. Knowing how the tech world operates, I'm guessing this is one of those situations where the original creator abandoned the project and the open source community had to step in and rename it to keep it alive.
You hit the nail on the head. It's a classic piece of internet history, really. PIL stands for the Python Imaging Library. It was this foundational, legendary tool built decades ago to let Python programs open and manipulate image files. But eventually, the original creators simply stopped updating it.
Life gets in the way, I guess.
Right. The code stagnated, and it stopped working with newer versions of Python.
But millions of programs probably still relied on it to process images.
Exactly. The community couldn't just let it die. So a group of dedicated developers took the original open source code of PIL and they created what we call a fork, a new, active, separate version of the project.
I see.
They named this modern, friendly successor Pillow. Today, for historical reasons, you still type PIL when importing the code, but the actual living library that developers install and use is Pillow, which is why the modern documentation lives at pillow.readthedocs.io.
That's a great piece of context. So Pillow is the modern lifesaver of PIL. But bringing it back to our data flow narrative, how does opening an image file relate to everything we just learned about safely opening text files and parsing CSVs?
If we connect this to the bigger picture, the foundational infrastructure of File I/O remains exactly the same. An image file lives on the hard drive, just like a text file. You still have to request a ticket from the operating system.
Okay.
You still have to safely open a pathway to it using the with Context Manager to prevent resource leaks. The only difference is the specific decoder ring you use once the data is inside your program.
So open is always the door. But depending on what's sitting on the table inside the room, you bring a different specialist with you.
I love that analogy, yeah.
Like if it's a spreadsheet, you bring your CSV expert to dodge the rogue commas. If it's a photograph, you bring your pillow expert to translate the binary data into a grid of pixels.
That is exactly how you should think about it. The tools change, but the infrastructure of moving data from deep storage into active memory is universal. Pillow lets you open that binary image, resize it, apply complex color filters to it, and then crucially use File I/O to save that manipulated pixel data back to the hard drive as a brand new image file.
It is genuinely amazing how scaling up the complexity, from a simple grocery list to a high-resolution photograph, doesn't actually change the fundamental rules of the system.
It really doesn't.
Let's briefly recap this journey we've taken through these slides. We started at the absolute gateway, learning how to request a ticket and safely unlock the door to our data using Open. We learned to rely on to act as an automatic, foolproof door closer to prevent our operating system from running out of file descriptors and crashing.
And once that data was securely inside our program, we stored it in a list.
Right. We then tackled the strict traffic law grammar of the machine, decoding the positional slashes and explicit keyword asterisks in the sorted documentation to organize that data safely.
Yeah.
From there, we graduated to the chaos of the real world, realizing that the CSV library is an absolute necessity to protect our tabular data from the destructive force of rogue commas and unpredictable edge cases.
And finally, we transcended text altogether. We discovered the open source history of PIL and Pillow, proving that the exact same file I/O principles allow us to decode and manipulate massive files of binary visual media.
It really changes how you look at the mundane files sitting in your computer's folders.
Yeah.
But before we wrap up, I know you always like to leave us with something to chew on. Building on everything we've covered, what is the final takeaway here?
I want you to think about the rigid boundaries we artificially place between these different concepts. We talked about reading spreadsheets with CSV as one task.
Right.
And we talked about manipulating images with Pillow as a totally separate task. But to your program, it is all just data waiting to be opened. So what happens when you combine them?
Combine a spreadsheet and an image.
Exactly. Imagine you work for a company with 1,000 employees. You could write a single program that uses the CSV library to securely open and read a massive spreadsheet containing everyone's name, department, and job title.
Okay, I follow.
Then, in the exact same loop of code, you use the Pillow library to safely open a blank corporate ID badge image template. Your program automatically prints each person's specific name and title from the CSV directly onto the pixels of the template and saves out 1,000 uniquely personalized, high-resolution ID badge image files in a matter of seconds.
Oh, wow. Okay, that brings it all together beautifully.
The boundary between a text file and an image file is just an illusion created by the icons on your desktop. Once you know how to safely open the door and bring the raw data into your program's working memory, you can mix, match, and transform it however you want. The only limit is the logic you apply to it.
The boundary is an illusion. I absolutely love that. It really makes you realize that the next time you casually double-click an icon on your desktop, you aren't just opening a file. You are triggering a massive orchestrated sequence of events.
A whole chain reaction.
Yeah, a symphony of open tickets, automatic safety locks, complex data parsing, and binary decoding, all happening seamlessly in the blink of an eye. Thanks for exploring the digital blueprints of that magic trick with us today. We'll catch you on the next deep dive.